myself Bhumi Patel, Assistant Professor at LJ Institute of Engineering and Technology in the Department of Electronics and Communication. Today's our topic is the time response analysis for the second order system in the unit number 4, the performance of the feedback control system. So first of all, we know about what is the exact second order system response. So for that, we have considered a second order system with the unit step input, and we can take all the initial conditions as 0. So we can get this type of response, where we discussed earlier. MP is known as the peak overshoot, TP is known as the delay time, T is known as the peak time, TS is known as the cycling time, and TR is known as the rise time. Okay, so first of all, what is the definition of the delay time? So delay time is the time required for the response to reach 50% of the final value in the first time. So here you can see that in this graph, we can define the final value as 1. That means C of t that is equal to 1. So if my output will reach at 0.5 value, this time is known as the delay time for this particular system. So the delay time is the response will be reached the 50% of the final value, and the equation to find out the delay time, that is equal to Td is equal to 1 plus 0.7 zeta upon omega n. So using this equation, we can find out the delay time for this particular response. Now the second one is the rise time. Okay, what is the rise time? It is the time required for the response to rise from 10% to 90% of its final value for the overdamped system, and 0% to 100% for the underdamped system. Now what is the overdamped system and underdamped system? That we have to study in the last session, when we can put the different value of zeta, we can get the different response. We can take the 4 case where the zeta is equal to 0 or between 0 to 1. We can get the critical damped system, undamped system, overdamped system, and underdamped system. So if my system is overdamped, rise time will be 10% to 90%, and if it is underdamped, the rise time will be 0 to 100%. So the equation to find out the rise time, TR, that is equal to pi minus 5 upon omega n under root of 1 minus zeta square. Now 5, that is equal to tan inverse under root of 1 minus zeta square upon zeta. Now the third one is the maximum overshoot. What is the maximum overshoot? So MP is the maximum peak value of the response curve measured from the unity. So if we have to find out the value of MP, so percentage of MP, that is equal to C peak time minus C infinite upon C infinite. So the equation of the MP, that is equal to e raised to minus pi zeta upon under root of 1 minus zeta square into 100%. How we can get this type of equation? That we have to study in the derivation of the peak overshoot. The fourth one is the peak time. Peak time is simply the time required by the response to reach its first peak. Now what is the maximum peak overshoot? It is the maximum error during the transient response, and the time required to reach the maximum peak, that time is known as the peak time. So equation of the peak time is Tp, that is equal to pi upon omega n under root of 1 minus zeta square, and omega n into under root of 1 minus zeta square is equal to omega d. So equation of Tp, that is equal to pi upon omega d. Now the sixth one is the cycling time. It is known as the Ts. So this is my cycling time response. So in the transient response, we can get the maximum peak overshoot. After some time, my response will be stable. So the settling time is defined as the time required for the transient response to reach and stay within prescribed percentage error. So after some time my output data will be steady. So this time is known as the settling time. If we want to find out the settling time, the equation is Ts is equal to 4T. Now what is the 4 time? So the settling time for the second order system is approximately 4 times the time constant T, that is equal to 4 upon zeta omega n, where zeta is the damping ratio and omega n is the natural frequency. Okay, so using this different parameter, we have to find out this second order system response. And the sixth one is the steady state error. It is known as the ESS. So it is the difference between the actual output and the desired output as time t tends to infinite. If we want or we fix the actual output 1 and we can get the output 0.8, so the steady state error will be 0.2. So if we want to find out the steady state error, so the equation is ESS is equal to limit t tends to infinite r of t minus e of t. Okay, so using this different equation, we can find out the damping ratio, natural frequency, rise time, peak overshoot, and the cycling time. So we can take one example. Example is given here. The open loop transfer function of the servo system with the unity feedback is given by g of s, that is equal to 10 upon s plus 2 s plus 5. And here the unity feedback is given. So the value of h of s is equal to 1. We have to determine the damping ratio, undamped natural frequency of oscillation, and what is the percentage overshoot of the response to the unit step input. Okay, so they will given the equation g of s, that is equal to 10 upon s plus 2 s plus 5, and unity feedback is given, so value of h of s is equal to 1. So the characteristic equation will be like that: 1 plus g of s into h of s is equal to 0. So 1 plus 10 upon s plus 2 s plus 5 into 1 is equal to 0. Okay, so we have to simplify this equation, so we can get s plus 2, s plus 5 plus 10 is equal to 0. So s square plus 7x plus 20 is equal to 0. This is my equation number 1. Now, we can compare this equation number 1 with the second order standard equation. So the equation is s square plus 2 zeta omega n s plus omega n square is equal to 0. This is my equation number 2. Now compare equation number 1 and 2. So we can get omega n square, that is equal to 20. So omega n is equal to under root of 10t, and value of under root of 20 is equal to 4.472 radian per second. Now we have to compare the second term. 2 zeta omega n s is equal to 7s. S is cancelled out, so we can get 2 into zeta into 4.472 is equal to 7. So we can get zeta 0.7826, and percentage of MP, that is equal to e raised to minus pi zeta upon under root of 1 minus zeta square, that is equal to e raised to minus pi into 0.7826 upon under root of 1 minus 0.7826 square. Simplify this term and we can get MP 1.92%. So using the value of damping ratio and natural frequency, we can easily find out the value of percentage peak overshoot. Clear? Thank you everyone. If anyone have doubt regarding this topic, you have to contact me in my email